Okay, I'm on VFPM practice problem number 2. I've got a picture here with a mass on a 20-degree slope. We know about two coefficients of frictions, a static and a kinetic, and of course that'll depend whether it's moving or not moving. A light string, in other words a string whose mass we don't care about, over an ideal pulley, which means the pulley has no mass too. The block hangs at 2 kilograms, and the goal is, as the string pulls parallel to the surface, what's the minimum mass sitting on the hill so the thing stays at rest when we let go of it. So I'm going to think about the force diagram here. I know that this object is going to have a weight that's going to go straight down. What I really probably care about is not that weight per se, but is the components of that weight vector. So I'm going to think about what the components of that weight vector might look like. So I'm going to draw those as dotted lines. I know I've got a into the hill component, something like this, and I've got a down the hill component, something like that. Of course, I'm going to pull now this force out of my picture just so I don't get confused with that extra force. I know that as a result we also have a normal force, and we know that normal force balances this into force, so we know those two are going to match. Of course, the goal is that we want it to remain at rest, so that means that the tension pulling back up ideally would be the same as the down the hill force, but we also have the possibility of friction in here, and if this thing is going to start trying to move up the hill, we could also have a friction force down the hill. Of course, the opposite end of our tension is going to be over here on the 2 kilograms, so those two will match. And then the last force I'm going to also draw will be the weight of the 2 kilogram mass going down. Now let's go in and label some of those things. So again, this is normal, this is tension, this is also tension, this is weight of the 2 kilogram mass, and these are the two components of the thing called M, and we're going to call this friction. Okay, so what's the minimum mass of the system will remain at rest when it's released? So sitting at rest, we can talk about what it would take for it to be an equilibrium, and it looks to me like that would mean these forces have to balance. That is, if we think about the net force on object M, well, down the hill I'm going to have a positive component, so I'm going to have M, mass of M, G, sine of 20, I'm going to call it theta for now, that's one of them, plus a friction force, which is also down the hill, and then minus, going the other way, the tension. So those are all the forces acting on that object. And I know that if we're going to have the system remain at rest, I know that needs to be equal to 0. So I think what I'll do is I will just set that equal to 0. So I know 0 is mg sine theta plus the force of friction minus the tension. Now if we take a look over at this side, we know that tension has got to be equal to m2g. So I can write this again, but I can replace tension with m2g. Now if it's going to remain at rest, that is going to be the static friction, not the kinetic friction. So I also can write an expression for the friction force. I'm going to do that over here on the side. We know force of friction is normal times coefficient, and I know the normal force has got to be equal to the into the hill component. Again, this is the mg cosine component, so I know that Fn is the same as mg cosine theta, this force down here, which means we can write this whole expression right away into our equation up on the right. So now I'm going to go back here and do this again. So the net force has got to be 0. We know mg sine theta, we happen to know that number, fine. The friction force is mu times Fn. Well, mu, and again we talked about it being static because there's no motion, Fn is equal to mg cosine theta. And again, these m's are the mass up here labeled m, so I'm just going to call them that. And then minus t, the tension, what we know is equal to m2g, which is really a 2 kilogram mass times G. So now what we are left with is, gosh, a statement of equilibrium, and you know what? This whole thing only has one unknown. The only thing in here we don't know is the M value. I'm going to take a minute and clean it up. I'm going to put M2G on the other side. Those are both numbers. Over on the right side, I've got mg sine theta plus mu static mg cosine theta. And the best news is I can just pull an m out of that and have everything else in a big old parentheses. So m2g, and at the same time I'm actually going to take that parentheses and stick it over on the other side on the bottom in one shot. So I'm going to take all the things I distributed or undistributed, and I'm going to stick them over here. So if I take the m out of here, I've got g sine theta. That's a theta, wow. And then plus mu, and again if I take the m out, I've got g cosine theta. Again, this looks a little messy. It cleans up a lot. I notice the g's all go away. So just for fun, I'm going to make the algebra clean up a little bit, toss it over here on the other side. I can divide a g out of everything, and it looks like m2, which is just 2 kilograms on the top. On the bottom, it looks like sine theta, which is also a number because we know the angle is 20 degrees, plus mu, which is also a number because we know it, times the cosine of 20 degrees. All right, I'm going to grab a quick pause and grab my calculator. And after a little calculator action, I come up and see that that's about 2.1 kilograms. About 2.1 kilograms for the mass. Again, there was some messy algebra there, but if we look back, the point was, hey, we found equilibrium. Friction plus down the hill equals tension. And then we walked through and came up with a mass. All right, nice job.